What if I told you your deepest thoughts aren't just yours anymore?
Genius. Scientists are now using AI to decode brain activity, transforming your mind into visible images. But with great power comes a dangerous question. And who gets to control it?
Imagine a world where your deepest thoughts, your perceptions, could actually be laid bare for others to see. Not just guessed at, but visualized. Welcome to a deep dive into, well, one of the most intriguing frontiers of science and technology right now. We're talking about reading the human mind, specifically how scientists are getting brain activity translated into visible images. Our mission today is really to unpack the science behind this so-called mind-reading AI, look at some surprising applications, and crucially tackle the big ethical questions it's raising for all of us. So let's start with the core breakthrough, okay? The ability to reconstruct images directly from brain activity. It sounds like pure sci-fi, doesn't it?
It absolutely does sound like sci-fi, but you know it's rapidly becoming science fact. There's some groundbreaking research, particularly from Radboud University in the Netherlands, that's really pushing the boundaries here.
Radboud University, right?
Yeah. They're using functional MRI scanners, fMRI, sometimes even combined with implanted electrode arrays in very specific cases to capture brain activity.
And then turning that activity into pictures.
Exactly. They translate it into actual visual images.
Okay, let's unpack that a bit.
Yeah.
How does the AI actually do that? Is it magic? What's going on under the hood?
Not quite magic, but it's definitely clever stuff. The technique is often called deep image reconstruction. You can kind of think of it like a team effort between different AI systems.
Team effort.
Yeah, it combines something called feature decoding from those fMRI signals you get from the scanner.
Okay.
With really advanced image generation methods from machine learning. We're talking things like deep neural networks or DNNs.
Right, the things that can generate those incredibly complex images we see online.
Precisely. Those are like the artist AI, and then you often have generative adversarial networks, GANs, acting almost like an art critic.
A critic? How so?
Well, the GAN pushes the artist's DNN to make the generated images look incredibly realistic, almost indistinguishable from a real photo sometimes. It helps ensure the output looks natural.
So the artist creates, the critic refines.
Yeah.
And how does the brain activity fit in?
So the core process involves the AI basically, sketching out an image, then refining it over and over, pixel by pixel. It keeps adjusting the image. Until the AI's internal features of that generated image become really, really similar to the features it's decoding from the person's brain activity at that moment.
So it's matching the AI's thought to the human's thought, visually speaking.
That's a good way to put it, yeah. And often, a deep generator network, a DGN, is working behind the scenes just to make sure the final reconstructed images look like plausible natural scenes, not just, random noise.
That's a brilliant explanation, the artist and critic working together. You mentioned feature decoding. What exactly is the AI decoding from the brain signals? Is it specific patterns for, say, a cat versus a car?
Exactly that. Feature decoding essentially means the AI learns to spot specific patterns in the fMRI data that correspond to different visual elements.
Like edges or colors?
Yeah, things like edges, curves, textures, but also maybe higher-level concepts like human face or building. It's like learning the brain's unique signature for different visual components.
So it's not reading words, but the building blocks of what we see.
Precisely. It's understanding the visual components your brain is processing.
So, okay, with this incredible tech, what have they actually managed to reconstruct? Could we see, like, someone dreaming about their breakfast?
Well, maybe not breakfast details just yet, but they've had real success reconstructing both natural images, like things people were actually looking at, landscapes, animals.
Wow.
And also artificial shapes. And in one really impressive study, researchers managed to reconstruct specific letters of the alphabet someone was thinking about.
Letters? Seriously?
Yeah, they actually spelled out the word neuron purely from brain activity patterns.
Neuron? That's almost too perfect.
Yeah,
What does that tell us about how precise this can be?
it suggests a really remarkable level of precision, right? The brain activity for each letter, while probably subtle, was distinct enough for the AI to pick out and reconstruct accurately.
Amazing. What else?
And more recently, there's been a big focus on reconstructing facial images directly from fMRI data.
Faces? Like specific people?
Getting there. The research has been able to maintain the consistency of what they call semantic characteristics. So things like gender, male or female, or whether the person's mouth is slightly open, or even if they're wearing lipstick.
You're kidding. It can pick up lipstick?
Apparently so. They reported achieving about 84% accuracy in matching these kinds of attributes, which is, well, it's pretty astonishing when you think about capturing that level of nuanced detail just from blood flow patterns in the brain.
84%?
Yeah.
That level of detail is genuinely mind-boggling. But, it sounds incredibly complex. This isn't something you can just, walk into a clinic and get done tomorrow, right? There are big hurdles still.
Yeah, oh, absolutely, huge hurdles. While it's incredibly impressive, this kind of technology typically requires really intensive training.
Training? For the AI or the person?
For the AI, based on the person. We're talking something like 20 hours of fMRI scanning per participant to gather enough data.
20 hours? Wow.
Yeah. So it means it's definitely not possible yet to just, bring strangers in off the street and read their minds instantly. Generalizing the models to work accurately across different people is still a massive challenge.
Because everyone's brain is wired a bit differently.
Exactly. Every brain has its own kind of unique footprint or way of representing things, so it requires extensive personal calibration for now. It's very much a personalized process at this stage.
That makes total sense. So not quite the mind-reading helmet from the movies.
Not yet.
Yeah. But this ability to visualize thoughts, even in this personalized way, is just one part of a much bigger picture, isn't it? How our brains encode information generally. Which brings us to this broader idea of neural decoding.
It does, yeah. Neural decoding is really the wider field of trying to interpret the brain's own language, how it encodes information from the outside world, and how we can learn to, interpret that code.
And fMRI is key to that.
fMRI technology is absolutely central here. It's non-invasive, which is a huge plus.
Right, no surgery needed.
Exactly. And it offers pretty good spatial resolution. It can tell you where in the brain things are happening. It works by measuring tiny changes in blood oxygen levels.
The Boldy signal? I think I've heard of that.
That's the one. Boldy signals. These signals are basically an indirect indicator of neural activity, where the brain cells are working harder and demanding more oxygen.
So by tracking that oxygen use, you can map brain activity.
That's the idea.
Mm-hmm.
And this capability lets scientists decode all sorts of mental states from these activity patterns, going way beyond just what you're seeing.
Like what?
Well, potentially things like memories being retrieved, semantic knowledge, like knowing a cat is an animal, emotions, maybe even aspects of dreams.
Dreams.
And even potentially inner speech or intentions. The basic approach is you record brain activity while people look at things, or think about things, or feel things, and then you train sophisticated algorithms, machine learning models, to find the patterns in the brain data that reliably correspond to those experiences or stimuli. You're essentially building a statistical model of how that brain represents the world and its internal states.
Okay, now here's where it gets really fascinating. Fascinating for me. We talked about reconstructing what the brain sees. But dreams, they're so abstract, so personal. How does this research even begin to touch on something like dreaming?
It's a great question. And there's a really interesting parallel being drawn now between these generative AI models we talked about, like Midjourney or DALL-E that create images.
Yeah.
And the process of human dreaming. Both systems, the AI and the dreaming brain, process absolutely vast amounts of information they've previously encountered.
Right. Their training data or life experiences.
Yeah, exactly. And both create new outputs, images for the AI, dream scenarios for us, through what you could describe as probabilistic associations. They're essentially, dreaming up new content based on patterns and connections learned from past data.
So our brain is like an AI image generator when we sleep.
Some researchers are proposing something quite like that, yeah. They suggest that maybe the brain's visual cortex acts in a generative way while we're asleep, much like these AI adversarial networks sort of freely producing novel imagery.
Okay.
But then when we're awake, the same visual cortex acts in a discriminatory way. It's focused on accurately perceiving and interpreting the external reality coming in through our eyes.
Wow, that's a mind-bending idea. Generative when asleep, discriminatory when awake. The brain switches modes.
Precisely. That's the analogy being explored. This perspective implies that when we sleep, we're sort of seeing with our brain's imagination, maybe similar to how Midjourney creates images from text prompts.
Right?
Whereas our waking vision is more like, using a high-resolution a Canon camera, as one researcher put it, trying to capture objective reality as accurately as possible.
That's a powerful metaphor, seeing with imagination versus seeing with a camera.
It really is. It gives us a potential framework for thinking about how our brains construct visual experiences, whether they're triggered externally or generated internally.
What really stands out to you about this comparison? I mean, the idea that our sleeping brain is basically an organic Midjourney.
Yeah.
It's pretty striking. Does this change how we should think about consciousness, maybe? Or even reality itself?
Well, what stands out to me is the suggestion of this deep structural similarity, potentially between artificial generative processes and biological ones. It sort of hints that creativity or synthesis of new ideas or images might not be some mystical property exclusive to human consciousness, but perhaps an emergent property of complex systems processing vast amounts of data, whether that system is silicon-based or biological neurons. It definitely challenges our intuitive feeling about where novel thoughts or dream images come from.
In a consciousness angle.
Yeah, I mean, if AI can convincingly dream up new content in a way that seems analogous to our dreams, it does prompt reflection, doesn't it, on the computational underpinnings of our own subjective experiences. And maybe the line between our internal reality and external perception isn't quite as solid or fixed as we usually assume.
And maybe those probabilistic associations are running silently in the background, even when we're awake.
That's another fascinating thought. Yeah. What else is being generated or simulated that doesn't quite reach conscious awareness?
It really makes you think, and then this discussion, it naturally leads us beyond just visualizing thoughts to the whole field of brain-computer interfaces, BCIs. This seems like where neural decoding gets really applied, right?
Absolutely. BCIs are kind of the umbrella term for any technology or method that can record or even modify human neural activity.
Record or modify.
Yeah, and often the goal is to translate those brain signals into some kind of tangible feedback or into commands to control external devices. Think of it like a direct communication bridge between the brain and, say, a computer or a prosthetic limb, or even potentially another person's nervous system in some experimental setups.
A direct bridge.
Yeah.
And you hear a lot about their potential in rehabilitation.
Definitely. Their role in neurorehabilitation is probably one of the most impactful areas right now. BCIs offer this unique technological way to basically bypass damaged motor pathways in the nervous system.
So if someone's had a stroke or spinal cord injury?
Exactly. It allows patients to translate the neural signals associated with their intention to move into actual feedback or control, even if their muscles can't physically respond anymore.
That must be huge psychologically, just seeing something respond to your intention again.
It really is. It can allow for much earlier rehabilitation after brain damage, potentially providing options for patients who maybe can't engage in traditional physical therapy right away. And crucially, it helps fight against the negative effects of just not using a limb. Disuse atrophy. Learned non-use.
Right, the use it or lose it principle.
Precisely, and it's thought to actively promote neuroplastic processes, helping the brain to reorganize and potentially recover function. We're starting to see some really promising real-world potential, like restoring finger and arm movements for individuals with quadriplegia. Using these hybrid systems, combining BCIs with robotic hand exoskeletons.
That is genuinely life-changing stuff. But if the potential is so huge, what's holding back wider using clinics? It still seems quite niche, doesn't it? Are there big challenges?
Oh, definitely. There are significant hurdles for widespread clinical adoption. A key one is just the speed and effectiveness of learning to use a BCI.
It's not intuitive, I guess.
Not usually, no. Imagine trying to control a cursor on a screen just by thinking. It takes considerable practice and concentration. So making the hardware and software really user-friendly is critical.
And keeping people motivated.
Absolutely. Providing feedback that's engaging and not just, tedious is really important, and the tasks need to be adaptive, challenging enough to promote learning, but not so hard that people just give up. These are big engineering and user experience challenges.
So how are researchers tackling that?
Well, one approach being explored is using multimodal or maybe multi-stage BCI systems. For instance, you might start the initial intensive learning phase using more sensitive but less practical neuroimaging tech, like fMRI, or maybe even TMS, transcranial magnetic stimulation.
Okay.
To get really clear signals in the lab. Then once the person gets the hang of it, you might transition them to a more practical wearable system, like EEG-based BCIs that they could potentially use at home.
So start with the high-tech stuff, then move to something more portable.
That's the idea. Making it more accessible and effective outside of highly specialized research labs is the goal.
And this idea of the brain generating images, like we discussed with dreams, is that concept also being applied to AI itself? Can AI have mental imagery?
In a way, yes, and it's fascinating how it draws parallels to how we think humans reason visually. AI cognitive architectures, like one called SOAR, for example, are being augmented with mechanisms specifically designed to support reasoning using different kinds of internal representations.
AI thoughts?
Kind of. Symbolic representations, but also quantitative spatial ones, and even visual depictive representations, basically internal pictures.
So the AI can see things in its mind's eye.
Effectively, yes. These AI agents can use what are called imagery operators to construct mental images, transform them, generate new variations, and even inspect them internally to extract information.
Wow. Can you give an example?
Sure. Imagine you have robotic scouts assessing a complex situation, maybe a battlefield or a disaster zone. Instead of only relying on what their cameras see right now, they could use these imagery operators to mentally simulate the terrain based on map data, envision possible enemy movement paths, or even simulate what the view would look like from different vantage points to figure out the best observation post.
So it's like running a simulation inside its own head.
Exactly. It's a form of mental simulation for AI. It dramatically enhances their ability to solve complex spatial and visual problems without having to physically try out every single possibility. They can pre-visualize scenarios, optimize plans, much like a human might mentally rehearse a complex task before doing it.
That is a massive leap.
Yeah.
Applying our understanding of our own minds to make AI smarter.
Okay, but this power, visualizing thoughts, interfacing directly with brains, AI simulating mental imagery, it inevitably brings us to the critical ethical questions. Because, with great power
comes great responsibility indeed. And it's really important here to address the mind-reading hype head-on.
Right, separating the science from the science fiction. Precisely. While the progress is genuinely rapid and exciting, you do see claims, sometimes in the media, sometimes even from experts, that lean pretty heavily into what some ethicists call speculative ethics.
Speculative ethics, what's that?
It's often characterized by this kind of if, then, therefore logic. You construct these quite hypothetical, sometimes far-fetched future scenarios.
Like dystopian futures where everyone's thoughts are read.
Exactly. And then use those imagined scenarios to argue for, say, brand new human rights or drastic preemptive bans today. Now, the intention might be good, protecting us from potential future harms, but it can sometimes lead to, unjustified alarmism that could actually stifle valuable innovation and maybe distract from the very real ethical issues we need to tackle now.
Okay, so what are the significant real ethical and legal concerns we should be focusing on right now?
There are several really crucial ones. First and foremost is privacy. Neurodata, that raw information generated when you monitor brain activity, is potentially a uniquely sensitive category of personal data. It's not just data about what you do or what you buy, like traditional big data. It's data potentially reflecting your internal mental states, your perceptions, maybe even your cognitive abilities, vulnerabilities, or intentions.
That feels much more intimate.
It really does, and it's incredibly valuable. You can imagine this neurodata being integrated into big data processing by companies, by governments.
To do what?
To optimize profits, target advertising with scary precision, maybe influence political campaigns, or assess potential employees or insurance risks. This raises really fundamental questions. Should this neurodata just be treated like any other personal data under existing laws like GDPR?
Or is it different?
Or is it so fundamentally private, so close to our inner selves, that it needs its own specific, much stricter regulations, maybe even outright prohibition on certain types of collection or use?
That's a huge question. Our thoughts is the next commodity. What about misuse?
Surveillance, manipulation.
Oh,
That's the second major area, definitely. There are very legitimate fears about these kinds of AI models trained on brain data being used for things like coercive interrogations.
like a foolproof lie detector.
Potentially, or even worse, or used for widespread surveillance, maybe not just for criminals, but for monitoring employees, citizens. Concepts like neuroliberalism or surveillance capitalism are being discussed.
What do those mean?
They point to concerns about leveraging insights from neuroscience gleaned through these technologies to subtly influence people's decision-making, maybe nudge their behavior for commercial or political gain, perhaps in ways they aren't even aware of.
Wow.
Imagine, for example, brain metrics derived from BCIUs potentially influencing hiring decisions or promotions or even firing someone. Is this person focused enough according to their brain data? Are they resilient enough?
That sounds discriminatory and deeply worrying.
It absolutely is, and this links directly to the third big issue: consent and autonomy. True, free informed consent. Well, think about it. If using some kind of neuro-enhancing device could significantly boost your cognitive performance in a super competitive job market,
Right. Give you an edge.
or if a BCI becomes almost essential for managing a serious medical condition, can you really give free consent to not use it? The external pressures, job competition, health needs, maybe even social pressure, if everyone else is doing it,
Or dependency.
or even developing a dependency on these devices. These things could subtly, or not so subtly, compromise your actual freedom to choose whether or not to have your brain interfaced with or monitored. It's not just about keeping secrets. It's about our fundamental right to self-determination, to mental integrity.
That's a truly chilling prospect, feeling forced to use these things, or losing the choice if you become dependent. So how do we navigate this? How do we avoid that unjustified alarmism that could halt beneficial research but also protect ourselves against these potentially harmful and irreversible side effects? Sounds like an incredibly difficult balance to strike.
It is a very delicate tightrope walk, yes. The real urgency, I think, lies in establishing clear, robust, and potentially quite stringent regulations and policies now.
before it's too late.
Exactly. Before these technologies become deeply embedded in our everyday lives in ways we can't easily roll back. These regulations need to proactively address the critical issues. Who controls the technology agency? Who gets to use it? Access? How do we ensure meaningful consent? How do we protect neuroprivacy? What are the rules around extracting and using brain data?
So we need the conversation happening broadly, not just among scientists.
Absolutely. It requires ongoing proactive dialogue between scientists, ethicists, legal scholars, policymakers, and critically, the public. We need continuous monitoring, updating risk assessments as the tech evolves, and a real commitment to responsible innovation. The goal has to be designing a future where these incredibly powerful tools serve humanity, empower us, enhance our lives.
Rather than controlling or diminishing us.
Precisely.
What an incredible deep dive. It really does feel like we've peered into a world that was pure science fiction just a short while ago, but it's unfolding right now. From AI literally reconstructing what we see, to BCIs restoring movement, and maybe even boosting cognition, to AI developing its own form of mental imagery. The pace of advancement is just breathtaking. So after exploring all this, what does it really mean for you listening right now?
Well, I think as we get better and better at understanding, decoding, and even influencing the brain's signals, that line, the line between what we perceive through our senses, what we imagine in our minds, and what can be externally reconstructed, or even perhaps influenced by technology, that line is becoming increasingly blurry, isn't it?
It really is.
And this raises, I think, a profoundly important question for the 21st century. In a world where AI might soon visualize our thoughts, and neurotechnology could potentially alter our mental states, how do we even begin to define, and how do we ultimately protect what might be the last true frontier of personal privacy?
The inner workings of our own minds.
Exactly. How do we safeguard that inner sanctuary? That's the challenge ahead.